Okay, let's continue from where we were. Start a new chapter. So show that the basis P1, P2, P3 is the basis for P3. So this is actually an example that we did previously, and so we proved that solution. So we prove that P1 of T, P2 of T, P3 of T, and P4 of T are linearly independent. So they are linearly independent. So that is what we proved previous. So prove those are linearly independent. Where we said C1 P1 of T plus C2 P2 of T plus C3 P3 of T plus C4 P4 of T equals to 0. And then we substitute these values of P1, P2, and P3. So C1 T minus 1 plus C2 T plus 1 plus C3 T square minus T plus 1 plus C4 T cubed plus T equals to 0. So once we open the brackets, then what we get is C4 of T cubed plus C3 of T square plus C1 plus C2 minus C3 plus C4 of T, and then plus minus C1 plus C2 plus C3 equals to 0. And then finally, when we check the coefficients here, then what we get is minus C1 plus C2 plus C3 equals to 0. And then C1 plus C2 minus C3 plus C4 equals to 0. And then C3 equals to 0 and C4 equals to 0. C4 equals to 0. Now, what we can see here is C4 equals to 0, C3 equals to 0. When you come and substitute here, then finally what you get is C1 and C2 equals to 0. So basically, then C1 equals to C2 equals to C3 equals to C4 equals to 0. All of them will be equal to 0. So they are trivial solutions. So then, so P1 of T, P2 of T, P3 of T, and P4 of T are linearly independent. Now, since polynomial of real coefficients is of dimension 4, or just dimension. So since dimension of P of 3 is equals to 4. So we found out that the number of bases here
are 4. So basically the dimension is equals to 4. Then B is a basis of P3.
So since it is a dimension, so we have all bases here. So therefore, P is a basis of polynomial of order.
Okay, finally, in this chapter, let's look at the last theorem. Is theorem 2.3. And if we let V be a vector space of dimensions n. Now, if H is a subspace of V, then dimension of H is less or equals to n.
Space of the dimension. So if V is the larger space, and we have a subspace which is a part of the large space, then the dimension of H can be less or equals to n.
So it can be less or equals to n. So we can prove this one briefly. So we prove this. So we can prove that if H has 0 vectors, if H has 0 vectors, then dimension of H in this case is equals to what? It's equals to 0. It's equals to 0. So, so dimension of H is less or equals to n. Is less or equals to. Now, number 2, if H is not equal, does not have this 0 vector, then we can choose a non-zero V1, which is an element of H. We can choose that since V1 is linearly independent, then we can find the vectors V2, V3, all the way to VP with the elements of H. So we can find the remaining vectors V2, V3 with the elements of H, such that V1, V2, all the way up to VP is the basis for H. And hence, dimension of H in this case is equals to what? Is equals to P. It's equals to
The number of bases there.
P. The number of bases are P. And therefore, since V1, V2, all the way to VP are linearly independent, then dimension of V is equals to n. Dimension of V is equals to n. Then we get P as less or equals to n, and therefore dimension of H is less or equals to n. H is less or equals to P. Any question after that? Okay, if there is no question, then let's come to the last chapter. Yeah, and in this chapter we're going to do, we get some time. Then we're going to do 5.1, 5.2, and 5.3. So I think we can get the three sections. They are very important, and basically you will use most of them in mostly in engineering and if you're doing computer. So what this course is actually so important when it comes to engineering, computer science, and what else? I think even biology. Getting biology. So once you do your project, then when you're analyzing your data, then you put your data in linear form. So once you put them in linear form, then you put them in a matrix form, and then you now analyze. So you either get the values of y, so you predict. So mostly these ones are for predictions. So you get y, and then you also get x. So that is why you predict y. That is when you predict y. So in computer science, if you're doing computer science, so basically, mostly you will need this course when you will be doing maybe neural networks. Neural networks. Yeah. So you take it seriously. Okay, now let's come to this section, which is eigenvalues, eigenvectors, and eigenvalues. Eigenvectors and eigenvalues. So this is not very hard. It's actually very easy, and we'll be using what we've learned in most of the other sections. So let's define what this means. So definition. What are eigenvalues and eigenvectors? Okay. So if we let A be an n by n matrix, a scalar lambda, which we always say lambda. Yeah, lambda. Is called eigenvalue. Is called eigenvalue if A is is called the eigenvalue of A if there exists a non-zero n-dimensional vector X such that AX equals to lambda X. AX equals to lambda X. AX equals to lambda X. In this case, the non-zero X is called the eigenvector of A, corresponding to the eigenvalue lambda. The eigenvalue. So that is the eigenvalue and eigenvector. So this is the eigenvector. This one is the eigenvector. So when you multiply the matrix A plus the eigenvector, then it should give you the eigenvalue by this vector here. So it should be similar. So there is this scalar value here, which you get when you multiply this and this and then factor out some scalar value there. That is what you get. For example number 1. Determine whether the given non-zero vector X is an eigenvector of the matrix A. If so, then find the corresponding eigenvalue of A. So determine whether the given vector X is an eigenvector of A. If so, then find the corresponding eigenvalue of A. Example number A. If we have this matrix A equals to 7, 4, minus 3, minus 1, and we have the eigenvector as 2 minus 1. So determine whether the given non-zero vector is an eigenvector. So in this case, then all we need to get is we need to find AX equals to lambda X. So we need to find AX equals to lambda X. So therefore, we need to multiply this matrix here with this. And then we see whether we're going to get lambda or factor out lambda here. Find this grammar equals to what we get. So we multiply AX, which is equals to 7, 4 minus 3 minus 1 multiplied by 2 minus 1 here. And what we get here is what? So what we get is 7 multiplied by 2 minus 4 multiplied by 1. And then here minus 3 multiplied by 2 plus 1 plus 1. And this is equals to 14 minus 4. This is 10. And this is 6 minus 6 plus 1, we get minus 5. Minus 5. So here, when we factor out minus 5, or when you factor out, when you factor out 5, then what we get is 2 and what? Minus 1. 2 and minus 1.
So what can we see from here? So it means that this is our x, and now this 5 is our what?
Is our eigen value. So our lambda equals to 5. Our lambda equals to 5. And then, so it means that, so our x is an eigenvector of A and or corresponding to eigen value 5, corresponding to eigenvalue. Are we to get up to that? Okay, another example. Number B, if we have our A to be equals to 7, 4 minus 3 minus 1, and our X to be equals to 2 and 1. So determine whether that is eigen vector corresponding to any eigenvalue. So we multiply the same way. So AX 7, 4 minus 3 minus 1 multiplied by 2 and 1. So what we get is 14 plus 4, and then this is minus 6 minus 1. And here we get 18 and minus 7. 18 and minus 7.
So are we able to factor out anything here to get this one?
Are we able to factor out? So therefore, we cannot factor this one. So then this is not equals to lambda 2 and 1. So it is not equals to. So therefore, so X is not an eigenvector. X is not an eigenvector. Another example, number C, if we have our A to be equals to 1 minus 2 minus 3, 1 minus 2 minus 3, 1 minus 2 minus 3, and our X to be equals to 1, 1, 1. Let's say this is our A and this is our X. Okay. A, and that is our X. Now, when we multiply this, so when we multiply, then what do we get? So 1 and 1 is 1, plus minus 2, and this is minus 2, so it is 1, minus 2, and minus 3. 1 minus 2, minus 3. Again, the same thing, 1 minus 2 minus 3. 1 minus 2 minus 3. So what do you get? So 1 minus 2 is minus 1. So we get minus 4, minus 4, and minus 4. Minus 4, minus 4, minus 4. So this is equals to minus 4, and then 1, 1, 1. So therefore, this vector x is an eigenvector of A corresponding to eigenvalue minus 4, corresponding to eigenvalue minus 4. Any question up to that? Okay, number D. If we have our A to be equals to 1 minus 2 minus 3, 1 minus 2 minus 3, 1 minus 2 minus 3. And then we have our X to be equals to 1 minus 1 and 1. So let's say this is our X and this is our A. So multiply the two. So what do we get? So this is equals to 1. The next one is plus 2. And then the last one is minus 3. 1 plus 2 minus 3. 1 plus 2 minus 3. And finally, we get, so 1 plus 2 is 3. So we get 0, 0, 0. So we get 0. So then this is similar to, we can factor out 0, and this is 1 minus 1 and 1. We can factor out 0. So actually, this is equals to what? This is equals to 0, x. So that is the same as 0, x. So therefore, x is an eigenvector of A corresponding to the eigenvalue 0, corresponding to eigenvalue. Okay, let's write a remark here. Now, to determine whether a scalar lambda is an eigenvalue of an n by n matrix of A, then to determine whether scalar lambda is an eigenvalue of an n by n matrix of A, then AX equals to lambda x. AX equals to lambda. AX equals to lambda x. If and only if AX minus lambda x equals to 0. Right. Then also AX minus lambda multiplied by identity. If A is an n by n matrix, then we can still multiply this lambda by the identity, which is also n minus n by n multiplied by x equals to 0. And then also we can still factor out x here, which you get A minus lambda in there. And then we factor out x equals to 0. Then, therefore, the scalar lambda is an eigenvalue of A if and only if AX equals to lambda x, if and only if AX equals to lambda x has non-trivial solutions. Has non-trivial solutions.
So in this case, for this one, for this lambda to be the eigenvalue of this, then we should not get trivial solutions. So we should give us
Solutions. So if it is giving us non-trivial solutions, then that means a minus lambda in x equals to 0 has non-trivial solutions. So this should also not give us trivial solutions. So it should not give us trivial solutions. For example, example number 1. Example number 2. Determine whether the given scalar lambda is an eigenvalue of the matrix A. If so, then find all eigenvectors of A corresponding to lambda, corresponding to lambda.
is an eigenvalue
Of the matrix. So number A, if we have our A to be equals to 7, 3, and 3 minus 1, and we have our lambda equals to minus 2. Our lambda.
Then let's see whether the given scalar is an eigenvalue of that A.
For us to see whether this is an eigenvalue, then it should not give us trivial solutions. So it should not give us the trivial solutions. So here, what we need to get is we need to find the solution of A minus lambda I. And in this case, since this one is a 2 by 2 matrix, then we multiply this one by the identity of a 2 by 2 matrix, and then x equals to 0. Equals to 0. So we need 1.
So therefore,
Our A is this, our A is 7, 3, and 3 minus 1, and then minus lambda, in this case, is minus 2, and then the identity is 1, 0, 0, 1. And then all this we multiply by what? By x equals to 0. Equals to 0. Then this will give us 7, 3, and 3 minus 1. And then minus, you can open these brackets here. You distribute the value of minus 2 inside. So you get minus 2, 0, and 0, and minus 2 there. X equals to 0. X equals to 0. Then now you can do what? Now, now subtract. So finally, what you get here is 7 minus minus 2 is what? Is 9. 3 minus 0, you get 3. 3 minus 0, you get 3. Minus 1 minus 2, you get what? Get 1. So that is what you get. And then now our x equals to what? Equals to 0. X equals. So now we want to find the values of what? We want to find the values of x. So we want to find the eigenvectors. So using so we put that one in augmented matrix form. So, and then we do what? We reduce completely. So we now put 3, 1 in an augmented matrix form, 0, 0. And then we reduce this one completely. So when we reduce this completely, then so reduce completely. Then what we get is 1 over 3, 0, 0, 0, 0. So that is what we get. Then, in this case, our basic variable is x1, and our free variable is x2. Free variable is x2, and therefore we have here x. Our new linear equation is x1 plus x1 over 3 x2 equals to 0. Then x1 equals to minus 1 over 3 x2, and therefore the solution set is our x will now be equals to x1 x2, which will be equals to minus 1 over 3 x2, and then our x2, which is our free variable, and this is equals to our x2 to be equals to minus 1 over 3, and then 1, where x2 is not equals to 0. Or x2. So we don't want to get trivial solutions. So x2. Therefore, our eigenvector, then our eigenvector is minus 1 over 3 and 1. So that is our eigen. Any question after that? Now, if we are given another example, and if we have a to be equals to 7, 3, 3, and minus 1, and then you have our lambda to be equals to 2. So we do the same way. Same way. So in this case, we want to get a solution whereby our a minus lambda I2 x equals to 0. So that is what we want to solve. So we substitute these values here. So 7, 3, 3 minus 1. So that is our a minus 2 here, 1, 0, 0, 1. And then our x there equals to 0. Then what we get here is now 7, 3, 3 minus 1, and then minus 2, 0, 0, and 2 there. X equals to 0. So when we solve this, then this will give us 7 minus 2 is 5. 3 minus 0 is 0. 3 minus 0 is 3. 3 minus 0 is 3. 3 minus 0 is 0. And then minus 1 minus 2 is minus 3. Minus 3. And then we have our x there equals to 0. So therefore, we now put this one in augmented matrix form, which is 5, 3, 3 minus 3, 0, 0. And then we reduce completely. So reduce completely. And what we get is 1 minus 1, 0, 0, 8, and 0. 0, 8, and so what you do is you can switch. So you can switch this and that, okay? And then you divide by 3. So you switch this one, so you can switch this, it comes up here, and then you divide by 3, get 1, that's 1, and then now. So once you reduce, you get that. So we can see from here that the basic variables are x1 and what? And x2. So we don't have free variables. So in this case, we will have the trivial solutions on. So in this case, we have the trivial solutions. So therefore, the solution sets x is equals to x1 and x2, which are equals to what? 0 and 0, which are equals to 0 and 0. And so therefore, since a minus lambda I to x is equals to 0, does not have non-trivial solutions, then lambda equals to 2 is not an eigenvalue of A. It's not an eigenvalue. So you can just say, since this one is giving us the trivial solutions only, then lambda is not. That's not how non-trivial solutions. Any question to that? Okay, that is how to get the eigenvalues and eigenvalues. Okay, now let's come to the next section here, which is eigenspace of the matrix. Number 2, the eigenspaces of a square matrix. The eigenspaces of a square. So let's define this one. So 2.1 definition. If lambda is an eigenvalue of an n by n matrix A, then the solution set of A minus lambda I n of x equals to 0 is called the eigenspace of A corresponding to the eigenvalue of eigenvalue lambda corresponding to eigenvalue. So if you're getting the solution set, which are eigenvectors actually, then the all of this is what we call index of A. It is composed of all the eigenvectors of A corresponding to lambda and the 0 vector corresponding to lambda and the 0. So this lambda is for example number 3. Find a basis for the eigenspace of the matrix A corresponding to the eigenvalue lambda, the eigenvalue lambda. If we have our A to be equals to 4 minus 2 minus 3, 1, 1 minus 3, 1 minus 2, and 0 there. And lambda to be equals to 3. Lambda equals to 3.
So find the basis. So we want to get the vectors in the solution.
So we want to get solution. So we actually want to get A minus lambda I, in this case 3, x equals to 0 vector. Equals to 0. So then our A minus lambda I3 is now equals to 4 minus 2 minus 3, 1, 1 minus 3, and then 1 minus 2, and 0. And then minus what? Since this is 3, we distribute it inside the identity 0, 3, 0, 0, 0, 3, 0, 0, 0, 3. And then we subtract. So when we subtract this, then we get 1 minus 2 minus 3, 1 minus 2 minus 3, 1 minus 2 minus 3. So that is what we get. So x equals to what? Equals to 0. Now we want to get the solution set. So now we want to get the solution set. So we reduce this completely. So when we reduce this one completely, then what we get is reduce completely. Then what we get is 1 minus 2 minus 3, 0, 0, 0, 0, 0, 0, 0, 0, 0. So that is what we get. So therefore, our basic variable is x1, and our free variable is x2 and x3. x2. So then our new linear equation here is 1 minus 2 x1 minus 2 x2 minus 3 x3 equals to 0. So then x1 equals to 2 x2 plus 3 x3, 3 x3. So we get our new solution set, which will be x equals to x1, x2, x3, which will now give us 2x2 plus 3x3 and our free variable, which is x2, and also our free variable x3. And therefore, this is equals to x2, which is 210, plus x3, which is 30, and then 1.
That's where, yeah. So these are actually eigen.
Okay, I'm preparing your what do you call it? Yeah, the practice exam for exam 3 and the final exam. So I'll post them in Moodle before the end of this week.